Good afternoon, everyone. Welcome to the second video of a many video part series on how to actually run Keras and TensorFlow in R. So specifically today we're tackling the problem of word embedding. So first of all, what is R, what is TensorFlow, what is Keras, and what is word embedding? So R is a programming language used a lot in data science, specifically for bioinformatics, and the whole bioconductor is basically run in R. While RStudio is the IDE, the integrated development environment. It's just a better way of programming that shows you, let's say, your script, your console, your environment history, and files, plot, and so on. So RStudio is the IDE for R. So next one is Keras. I didn't explain in the last video. Keras is basically a high-level API that can interact with many other type of lower-level programming language like TensorFlow. Technically, it's also an API. So Keras is the one that you interact with other program, so that it's easier for you to write your neural network. You can understand it like that. While the last one, TensorFlow. So TensorFlow is a way of organizing data so that it can flow around more efficiently, effectively, and most importantly, faster and so on. So Keras itself is written by one of the scientists that I forget the name. Let me just do it very fast. So it's a Python learning library written by yeah, it's actually not written in their main platform, which is interesting. So if I'm not wrong, they're maintained by here. Oh wow, there's no one that actually do it. Yeah, it's written by this person that actually maintained by it. While TensorFlow is mainly developed and maintained by Google and so on. So once we settle that, let's go into our RStudio. So the first thing is that the example I'm using here is actually from the RStudio blog, written in 2017. So more than 3 years away from now. And it's quite stable, it has been run many times. I believe that a lot of people have already used it in their project and so on. So the first thing that we need to do in this environment is try to figure out what is our workspace, what folder in Windows are we running on. Similar for things for Mac and Linux and so on. Your work directory, in this KWD, means which work directory you're running on. So you can run the first command to get your current work directory into a variable or an object. So in this case, I'm running it on my desktop. But of course, if you want to change it, you can just change it on the code over here. I'll sample my script on Google Drive, and I'll put the link to the script on the video description down below, so you are able to check that. And the second thing you need to download is that since you are running a word embedding file, we need to download a big word file. Basically, we need a big library and vocabulary for the machine to understand what we are training on. So this is both our training and testing example. I'll explain what later, so you can go ahead and just run this command to download the file. So when you are downloading a file, let me just talk a little bit on what is the meaning of word embedding and what is work2vec. Why are we running an embedding? What does that mean, and what we are trying to accomplish? So word embedding is one of the most popular representation of document vocabulary. So it's trying to make a single words represented as a series of vectors, and the meaning of word to vec over here. So word vec means vector, and if you don't understand vector, they are just multiple strings of number. So if you are familiar with plotting a graph, you have x and y coordinates, where 1 will be, let me just do my pen skill for a moment. So if you have a coordinate of x and y, it actually means a vector in the two-dimensional space. And if I give you the number 1, you actually know that immediately on the graph, if 1 is here, 1 is here, this vector will represent a dot right here. And if I give you another one called 2, we'll know the x-axis, let's say, sorry, I'm not very good in drawing with my mouse. And the second, so this is point A and point B. So point A will be here, point B will be here. So this is the meaning of vector. So we are trying to represent each word into a vector. So that's a basic my understanding of word2vec, while word embedding is trying to make similar word having a similar combination of vectors. In this case, I should go to this one. Let's create a new one. So in this case, what does word embedding trying to do is that we are trying to make similar words appear on similar space. So we already have the two-dimensional vector just now, point A and point B. Let's say you have cats as with the vector coordinates of 1, 1, and you have dog with the vector coordinates of, let's say, 1.1, sorry, 1.1, and maybe 1.1 again, because cats and dog, in terms of words, they are very similar to each other. So 1.1 over here. So this 1.1, 1.1. So you can see that cats and dog will appear very similar to each other. So 1.1 is around here. However, if you something come in and then something is not gonna be similar to these two, let's say you have a nation, so you have USA maybe, and you have another country, maybe Singapore. So you have these two countries which is similar to each other but very distant from cats and dog. So these two is what cluster, these two is a cluster, but two of them are very far from each other. So if you plot it in a dimension, in a matrix space or hyperdimensional space over here, maybe the USA will be here, while Singapore will be somewhere here, because end of the day, USA and Singapore are not that similar to each other. So you expect something like very similar to USA, maybe Canada will be here, maybe Malaysia will be here, and so on and so forth. So you also expect something like a verb, let's say eat, might be here, and you will say some sort of adjective like beautiful to be here. So you can see that maybe this part of the space is a verb, this part is a pet, this part is a country, this part is an adjective, and so on and so forth. So of course we'll have different type of adjective, we'll have different type of verb, and we have coffee, and so on. So we have very different type of word represented by that own cluster in a vector space. And of course I'm trying to do this here in only two-dimensional. In most of the word embedding we have more than one. In this case, the example given by the website over here, which is from Towards Data Science, is a 5-dimensional vector. So half is 1, 0, 0, 0, 0, A is 0, 1, 0, 0, 0, and so on and so forth. So we have 5 different words here with 5 individual vectors, and this will be plotted into a 5-dimensional space, and we'll be able to see from the cluster. So having a 2-dimensional space, of course, is very limited. But imagine you have an axis that go across like this, and you have a 4-dimensional, 5-dimensional, and so on. But the concept remains the same, because if they are closer to each other, they will remain somewhat the same. They will remain somewhat from the same context of a sentence, if that's, yeah, I think we can say it like that. So the second thing we need to know is what we call a cosine similarity, will be very important later when we talk about SkipGraham modeling. So what is cosine similarity? So cosine similarity is actually the angle in between two vectors. So we talked about just now on different cluster. Let me create a new file. So if you have two words, let's say one point is here, let's create 3 just in case, and you have one word here and one word here. So let's just draw the vector to point 1 and point B. You can see that the angle between them is actually quite small, means that they are actually closer in terms of space. So the angle might be 5 degree, 10 degree, and so on. So that will create a cosine value of this to be very close to 1, as you know that cosine 90 degree is equals to 0, and cosine 0 is equals to 1. So this cosine of this value over here will be very similar to 1. So cos theta. So this will be very closer to 1. However, if we compare to the other two, let me change the color over here. If you compare this line over here to the other line over here, you can see that the angle here is significantly larger. So we can kind of say that because the angle is larger, they're closer to a 90 degree, is going to be much lower than 1 and much closer to, let's say, 0. So the angle of this, the cosine theta over here, let's say it is 30 degrees. So cosine 30 degree, let's just get a calculator up here. So you have a cosine 30 degree. I don't really understand how to use this thing. Okay, I'm not identifying how to use this thing, but we can expect it to be somewhat between 0 and 1. So let's say they are halfway there. 45 degree is going to be 0.5 or something like that. I don't really remember this. I usually have my calculator. So the closer this value is to 1, means that these two words are similar to each other, while these two, let me just try the blue color, this and this are very, so A, B, and C. So we know A and B is similar to each other, while B and C are very far away from each other. Similarly, A and C will be far away from each other. So what you need to know, the smaller the value, the closer they are, the larger the value, the more different they are. So when we are trying to optimize our neural network later, we'll try to optimize for a smaller angle. So that's what you know before we go into SkipGraham. Okay, SkipGraham, sorry. Okay, so the first thing, of course, we need sampler library that is from R. So you can just install library, the packages over here, which is dplyr and readr and stringr. So these are very common for matrix manipulation and string manipulation, while readr is actually from read. Okay, let me just go through one by one. So dplyr is very useful for array manipulation. Readr is to read text file, CSV, into the R environment, while string R is very useful for manipulation of strings within the, let me check my audio level, so string R is very useful for manipulation of strings in the R environment. In this case, we are actually using a really big 5-foot txt file. So it's a text file, and it's actually quite a big file. It's 100 something megabyte if I'm not wrong, and about 300 megabyte when you try to load it into the RStudio environment. So we need some sort of automated way to try to actually manipulate this text before we feed it into our neural network, because it will be too big and it will be too much junk. So we are putting it into an object called review. So if you try to put a head 5, sorry, reviews with an S, so we can see that let's say put 10 so it's easier. So we have the first review of the product ID, we have user ID, we have profile name, we have helpfulness and all, and so but we only want the review text, because the rest of the things are not very useful for the calculation of word embedding. It would be good if you can further segregate the review score down and try to do word embedding based on positive and negative review. That will be further analysis after we have finished word embedding. But for the current current goal that we've set for this exercise, we just want the review text. So this command, which called review substring, is actually substring means that it actually calculate only from the first to the 12 characters within your first to 12 character every line for every single element inside your object. In this case, the first 1 to 12, we want it to be review text. If it's not equal, ignore it. We don't want to include in our next into our object. So you can see that we have 500 half a million here, half a million element. After I run this command, you can see that it has gone down to also around half a million elements. So we have removed all the junk. Actually, we can have a look again over here. So we only have the review text available to be for the training later on. So the next one, of course, we want to remove the first 14 characters, which is the review text, and all the things that are the same, because we don't want them to present into our training later. So this will remove it. Let's just have a look again. Yep, so that removed the review text and so on. And the last one, we want to encode our whole review file, which is this 187 megabyte file, into UTF-8. So this is just to help and make sure that later when we feed it down the road, we will be able to know definitely they are the same encoding. We will be able to feed this encoding into Keras and TensorFlow without causing problem. It might already be in UTF-8, depends on how you save the file and txt and so on. Okay, so let's just have a look again. So you can see that we have this, which is the first review. We have this as a second review. And if you want to view more, you can change the number. Anyway, and 1, 2, 3, 4, 5, 6. The first 6 sentences or paragraph of the review. So once we have all these sentences, we can actually start to calculate how many word vocabulary do we want to include. So we have talked about just now about this word representation. So that's not possible to use to have every single word with a vector, because it will be too much data to train, because a lot of time some word only appear once or twice within the whole vocabulary, and it's just really we don't want to waste computing power on those things, because it doesn't it doesn't have enough data to train. So what we do over here is that if I just let you see the number of unique words that we have in the first 200 sentences, we have about 500,000 of them. So only the first 200 we have around 33,500 different unique words. So if we actually use the whole thing and put the word vocabulary for the whole thing, it's gonna be a lot. So we're not gonna do that. So before that, we're gonna include the TensorFlow and library and Keras library that we have installed from our last video, and run something called a tokenizer. So what does a tokenizer do is that it actually convert individual sentence into a number, in the index number, you can say. So I got a wild hair for Taffy. In this case, maybe I will get encoded to 1, God will get encoded to 2, will get encoded to 3, 4, 5, 6, 8, and so on. But we only want to convert the 20,000 most most popular words within our database, because if you include more, you have to train more, and your table become exponentially bigger. You have to remember, every time you include a word, you have to be converted into a vector. So you include 10 more words, you don't just include 10 more elements, you include 10 times number of vectors that you specify for your matrix. So your matrix become exponentially bigger. So 20,000 depends on the project that you're running on. It could
narrator dialogue. Narrator exiting narrator.
I didn't do anything on narrator, so that's interesting. So the tokenizer will only convert the 20,000 most used words within your database, just to save a little bit on the computing power. And seriously, if they don't appear much, it's not worth the computing power to, let's say, to calculate a word that only appear once or twice. And with the number of, and with because of how machine learning works, if we have a small number of training sample, it will not be accurate anyway. So we are gonna just ignore them. So this is gonna take some time, because it's actually gonna pull in all the words, which is again 187 megabyte, and try to only find 20,000 most popular words and assign index to them. Okay, so then we'll have our library of 10,000 words. Because it is actually in Python, we can't actually see this thing properly. Yeah, that little bit of incompatibility between the two, so we can't actually see what are the words, but we'll be able to do that later, so don't worry about that. So the next two library that we include is reticulate and purr. Purr, we need it for map function, and reticulate allows Python to be run within the RStudio environment. It's kind of like, I don't want to say emulator, but it's kind of how you pipe Python code into R, and some of the functions and so on. So the next one I want to talk about is the function over here. It's called a SkipGraham Generator. So with that, I'm gonna redirect you to this website, which is Becoming Human over here. So how does the work-to-back SkipGraham work? So there are two different type of approach for word embedding, and one of it is called a SkipGraham. The other one is called a SIBO. So I don't think SIBO would be part of our the focus over here. Let's just talk about SkipGraham. So in this case, we have a series of words. The quick brown fox jump over the lazy dog, where we have a target in the middle and the context around it. So we want to know, let's say, I think this figure summarizes it very well. So the first training sample from the source type will be the quick brown fox. So we want to know about the properties of it will be based on quick and brown, because they're beside it. And if we want to know about the properties of quick, it will be from the brown, and the fox. So the context of the word, the meaning of the word, the feature of the word always be dependent on what word is around it. And if you always have the word, let's say brown, followed by fox, followed by dog, followed by any animal that you have, we know that it is related to a property of the animal, and so on. So you can adjust the word size. Now this example has a word size, window size of 5, where we take 2 before and 2 after. So you can see that how it is extracting fox with quick, fox quick, fox brown, fox jump, and fox over. So this is -2, this is +2. So we need to know that using the context around here to calculate the vectors for the target in front. So we're going to call them target and context. for our next training video. So basically every single sentence will be converted into all these training samples, and this is basically how does the SkipGraham generator works. So if you actually look at the SkipGraham generator, they are taking in the text, the tokenizer, which tell the neural network later which vocabulary are you using, the window size, which is what we saw just now, the size of this sliding window, and we have a negative sample. So negative sample, I'm not going to go too deep into it, is a way of increasing the probability for the rare words to get chosen, because when we do machine learning, there's a lot of randomization and sampling involved. So negative sample increase the probability of some rarer words to get chosen instead of always choosing and so on. So we might be able to choose, let's say, jumps over because is going to appear a lot of times in a lot of sentences and so on. So you can see the output of this is actually list x and y. So the SkipGraham generator will take all this thing and output a list of x and y. We can see it's x and y. So we are trying to train a neural network that make sure that these two words will generate a cosine similarity of closer to 1. Okay, so now comes the real Keras idea of how to actually make x and y having a low cosine similarity. So now we're actually going to go into the Keras languages and vocabulary and syntax, or whatever you call it. So we are trying, so now we actually start to build our neural network. Once we got the SkipGraham involved, we get our sample done, we get the tokenizer done. Now is the time where we build our neural network. So the first thing that we need in word embedding, obviously, is the embedding size. So that is the dimension of the embedding vector. So we talked about just now where this, what is that called? This example over here have each word convert to a 5 elements vector. So in this case, the author of the script actually uses 128, but feel free to change it as you wish, and you can see how it affects. The larger the number, the likely that you're going to overfit the data, and it takes a lot more computing power to run. However, the smaller number might not be able to separate the kind of vocabulary that you have. So it results in things get clustered together, even though they should be separate. So it gives you more resolution and so on. So the skip window is the sliding window size that we talked about just now. How many words consider from left to right, and number of sample will be the negative sample that we talked about just now, where increase the probability of the rarer words to get chosen to be more representable. So the two input that we're going to use is input target and input context. So input target over here will be the x, which is the target word over here. So the first row on the list, and context will be the second row on the list. So we have an input size of 1 because our SkipGraham generator only gave a 1x and 1y and so on. So for the embedding layer, it has to be the first layer after your input layer. So in this case, it will just be a standard thing where you have the dimension, the dimension will always be the input, the tokenizer number of words plus 1 because of the bias and how it actually works, while the output dimension will be your embedding size, which is exactly the number of vectors, because one word go in, it should be 128 numbers come out and so on. So input length is 1 because we only input one word at a time. So the next two is the flattened layer. So is the target winner, it's actually this one. So we actually put them into, we flatten the matrix into a vector because we want to have each of this target as a vector and context as a vector, and then the dot product calculate the cosine similarity between the two vectors and try to see if they are actually they are closer to 1 or they're closer to 0. So before we get our output, we just apply a sigmoid activation. So if you're not familiar with sigmoid activation, it kind of looks like this. So anything that got closer to 1 will get converted to 1, and anything that is not will get converted to 0, or the negative number will get converted to negative, and we usually just ignore them, because what we really want to train our network for is for things to get closer to 1, because everything that we feed into our network is actually next to each other. So it's kind of a semi-supervised approach for word embedding and so on, depends on how you classify the things. So these are just the way of how you put everything into our neural network model, and our model compile we use a binary cross entropy for the losses. add-on for optimizer and matrix for accuracy. So feel free to change this around and see what happens. So with that said, let's try to run this and see if it actually works. Well, it should. I actually tried many times before I actually film this, obviously. So in this case, you can see that our model 1 has 2 input layers. So this will take our context and our target. We have an embedding layer of 1 because there's one sentence, and 128 different vectors for each of the one sample. Because we have 20,000 plus 1 of the word size, which is a vocabulary from the tokenizer earlier, we have 262,500,000. So it's about a quarter of a million parameter to train. It's also how many elements we have in our word embedding matrix. Later on you will see that. So what does the flatten layer do is that they're trying to take a vector and take a matrix over here and try that into a vector. So layer 2 is actually come from input 3, layer 3 is come from input 4, and so on. So they will be able to, so you'll be able to get 2 vectors while you get the dot product of the 2 flattened layers, and finally we output a dot. So let's just demonstrate that again while drawing out. I think that will make things a lot easier to understand, at least for me. Just a disclaimer, I don't really fully understand how it works. It's just that from the many documentation, this is how I understand, and this is the one that makes a lot of sense. And if I do make it wrong or anything that is not 100% accurate, please do leave a comment down below, or so that we can learn from each other and so on. So the first thing we have is there's 2 input. One is the target, one is the context. So there's 2 input neurons in our embedding word embedding neural network in our model. Okay, so that 2 things will be, so they will be represented by the number in our tokenizer. One will have a number, maybe 56. This one will have a number, maybe 72, and that fits into an embedding layer. So the embedding layer will have 2 dimensions. Obviously, the first dimension will be the number, the word size that we have, which is 20,000 over here plus 1, which is the what's that called, the bias that we introduce into the matrix. And we also have 128 new vectors for each of our words. So what does the first thing do is that the input layer is 56 and this one is 72. So before that, let's complete the network first. I think it'll make things a lot easier. So the first output that we have is a flattened layer of 128 in the 8, and the second one we have is also another vectors of 128. And with these 2, we times them into a dot product, and from the dot product we apply another neuron for our output, and there will be some bias going and weight going into this as well. So everything is very similar, very familiar if you are from a machine learning network background. So the input layer go in, from all these 20,000, it choose what it is, the 56, maybe the number 56 column, it goes here, and this one 72, it goes here. So this will be the vector for our target, and this will be the vector for our context. So then we try to calculate the dot product between these 2, try to calculate the cosine similarity between these 2, and we see how the value, and we calculate it out. Is it 1 or is it completely away from 1? If it's not away from 1, the back propagation happens and it changes the value in this table, so that so that eventually we get a value of 1. So every time we fit in 2 elements and you try to calculate this table in every run, so that this table get run all the time, and then it changes every single step, so that it can optimize the value, where our 2 input context and vector, when we calculate the dot product and apply activation function, it will actually be 1. So this is what we are optimizing our network for. Okay, so once we're done, we actually can go into training. So when you declare a network in Keras, they actually automatically randomize all the input over here. So everything now is completely wrong. I wouldn't say wrong, it's just not accurate. So the next one after we compile is called a model feed. So in this case, we're using a feed generator because we're not feeding the whole thing inside at once. You randomly choose certain reviews over the other. So in this case, the original article, I think, do 100,000 steps per epoch. for about 5 epochs or so on. So it's gonna take a long time. It actually says in the article itself that even on a GTX 1070, it takes about half an hour per epoch. So I don't have much time, even though my computer is CUDA accelerated, my VRAM is too small, and it takes 4.5 hours for me to run 100,000 of them. So I'm not going to show you how to get the correct, the accurate model. I'm going to show you how to run a model. So I'm going to reduce the step per epoch to 50 and run an epoch of 10. That brings into our next point. What is the meaning of steps per epoch? So this is a complicated one. So we have our SkipGraham Generator, which is the one that we talked about earlier. So the step per epoch means how many reviews tags you want to run at one time. Okay, and how many epoch is how many steps you want to run. So let's say here we are running 10 batches of data. So we are fetching 10 batches of data. Each data has 50 different reviews, something like that. So 50 is a ridiculously small number, 10 is also a very small number, and if you want accurate data, you need to increase at least to 5,000-6,000 or so. So the total number that we can run based on the sample that we input here, which is 568,000. So the maximum number step per each bot and epoch we can run is actually 568,454 divided by the number of epoch. But of course, it's not a whole number. It's gonna give you an error. So if we certain time we can ignore certain things. So what we can do is actually just delete one character from here. So if you do want a really accurate data, you can actually run 56,845 for 10 epoch. And if you really are concerned with the accuracy and the model, you really want to overfit the data. Let's say you never need to include any new example into your network or model. You can actually just repeat the number of review. Let's say you have now, so this is one set of data. You can repeat this 10 times and then increase epoch by 10 times so that you get more runs on your data on your network, so that it get gradually more accurate. But I want you, it's going to take a lot more time. So let's just do our cheating thing for the beginning. Let's try 50 steps per epoch for 10 epoch over here. So the good thing about Keras is that actually if you go to the viewer down below, I run it beforehand. So this is the run that I had last time before I actually start viewing the video. So now it started a new one. So in every step it will show you what is the loss. The loss is the number that is not closer to 1, so that they got minus off. So the lower number of loss, the more accurate your data is. While accuracy is another equation to calculate if these two will correctly predict each other. So loss and accuracy are kind of the same concept, but just calculated differently. So in this case, our loss is about 50% with accuracy around 78%, which is doing surprisingly well compared to what I run last time. So yeah, it's great. Okay, that was interesting, but I will highly suspect that because of the little number of sample, when you run this with other sample, it might not work properly. So you can actually see the progress of our loss, where it drops down from 69%, which is a typical value when you start the network, down into now it's about 46%. And while the accuracy increases from 54%, which is 50% is just guesswork, so 54% is good enough for random chances, while our accuracy actually grew to 80%. So the original article actually can get an accuracy around 90% if you go for it long enough and you have enough computing power and patience to wait for it, and so on. So if you do not want to use this graph and you prefer easier graph, I usually like to use a scatter plot instead of a line plot, so that you can actually see how much each of them actually changes from one epoch to another. In this case, maybe you can cut it off at 8 epoch, because in reality, our step epoch maybe will be 10,000 and so on. I'm sorry for my mechanical keyboard, I like it very much. So it will be 100,000 and epoch maybe will be 100 or 10. So you can actually cut the number of training epoch once your data has kind of reached a stable state where it cannot increase in accuracy anymore and the loss cannot be decreased anymore. Okay, so that would actually finish our training. So the overall is doing quite well. We have a 43%, 0.43 loss and 80% accuracy and so on. So the next one is actually how to use the data. So we have done training our model. We have all our neurons we have all our words paired to their big factor. Now is how do we get it out? So in this case, we are able to use a command over here to actually join our embedding matrix with our words. So once you run all this command, you can actually see over here, you encase the bias that we introduced, and you can see one, just, taste, if, vary. So there's 20,000 rows, 21,000 plus 1 rows, and 138 total columns. Means view over here is represented by column 1 to column 128. So every single word will be represented by 128 elements and vector. So you can actually represent each word as a dot in 128 dimension hyperspace, if that's what you want to hear. Okay. So once we're done, we can actually use the same idea that we did earlier on the cosine similarity. So this functions over here is find similar words, is try to measure the similarity between one element and try to find the other element that have very similar probability, the very similar cosine similarity in this case. So in this case, we want to find the similar words with love. You can see love, this, of, is, I. Doesn't make a lot of sense. Let's try another word. Maybe cats. We'll expect to find, let's say, dog, kittens, and so on. Cats only, not for. It doesn't work. Let's try again. Let's try them. Doesn't really work. Yeah, doesn't really work because of the short training that we have, and most likely our training data is only applicable to the number of sample that we have on the first 500 sample that it chooses. Remember, they don't run it by sequence. They actually sample 500 from our 500,000 over there. So of course our model, even though it's very high accuracy, it's not the best model in the world. It's actually quite terrible. So you might want to run a much longer training and see if you can find a better answer about it. So instead of just running things one by one, we can also visualize our model with TSNE plot. So RTSNE means TSNE plot in R. So I got the things for that. So TSNE means for T distributed pseudo-static neighbor embedding. So it's a technique for dimensional reduction. I think if you are familiar with PCA, you might be familiar with the concept, because we want to reduce 128 dimensions into two dimension we can plot it out on a graph. So before I explain what is RCNC, let's go for our TSNE plot. So in this case, we can see that our data is clustered together in this shape, and this is reduction from 128 dimensional space into a two-dimensional space, which is V1 and V2, and things that are closer together are most likely to be similar to each other if you train your model correctly. So in this case, you can see breakfast and fat is here, flavor is here, and so on. And the problem is that because it's a word graph, we only take the first 500, because if you put too much of it, you can't actually see anything. They will just flood your whole thing in, and you can't really see anything anymore. So you can increase this by a little bit, maybe 700. So, but to be honest, you can't really see much, and for me, it would be easier to just do a clustering and see and just extract the whole thing from there. Just run again to change both sides, so that we have 700 to 700. So you can see that is a cluster over there on top and a cluster here on there. So you might ask, why does the shape changes so much when I increase a little more sample? So this is a little bit more complicated than just clustering and try to put similar things together. Remember that you're trying to reduce 128 different dimensions into two. So I think this website from this Steel Pub has a really good way of representing how does TSNE tells you about the clustering on the thing. So let's say you have 200 points with 10 dimensional and a perplexity of 60 and epsilon of 5. So you can actually run this, and you can see the number of steps actually will tell you there's different cluster you can find. This is not very obvious. Let's try this one. So you can see that with more number of steps, you're able to do different shapes of it, and based on the perplexity that you have and so on. Let's just crank a bit on dimension and so on. So you can see by adjusting the parameter over here, you are able to cluster them into totally different cluster, or they're totally mixed together. So that depends on a lot on the perplexability. Let's just talk about this as another example. So this is the original two-dimensional example, and if you run TSNE on different settings, this is increasing number of perplexity, which is kind of a perspective of how you look at the data. Imagine something like a perspective arcs, where you look at it from a different dimension, it will look totally differently. So imagine you have a three-dimensional space and you move your head around it and look at it differently. But of course, you're doing it in 128 dimensions. So it will actually look very different. So if you adjust your perplexity wrongly, you get a mix-up data. If you adjust your perplexity in the most optimized manner, you can actually see the most distinct clustering among your data set. So the step number, of course, also affect the way that you do things, and yeah, it will actually it will change a lot of things. And the best thing that I can find on how to optimize this plot is actually just try and error. So try different settings and see if you can get a better clustering and so on. So I'm basically done with the script. So what can we do with this data? So for me, the most useful thing in word embedding is the embedding matrix, where you can of course run LSTM, where you can actually build a sentence, or you can actually have the thing try to read the sentence and understand if this sentence is similar to another sentence and so on. But the ultimate goal is to obtain this graph where you have every single word represent as 138 vectors, and everything downstream will most likely be based on this embedding matrix. And again, you know, you don't have to stop here for word embedding. There's a way where the downstream will affect the upstream and how you optimize the matter and so on. So I think that's basically conclude the idea of word embedding. There's a lot more things you can do on this data. You can run a heat map on it. You can run many different type of clustering on it. You can build a sentence and try to see how does the thing change. You can run different colors, and you know, there's a lot of things that you can do. But hopefully, I think you learn a little bit from word embedding. I definitely does. So I will put the link in the description down below, and you can go home and try to run this on your own computer. Oh, one last thing before I forgot. So there are installation here where my TensorFlow and Keras is run on GPU. If your GPU has a very low VRAM, don't bother. It's not going to make too much of a difference. And also because we are using a SkipGraham Generator, our batch size is pretty small. It would not GPU acceleration would not make much difference to the idea. I think I have nothing to say. So thanks for watching. I'll see you in the next one. Bye.